So this is the plan for today. So I will tell you about crown decomposition and how to use crown decomposition to obtain kernels for vertex cover, for maxat, and then I will speak about linear programs, and then how the Trotter theorem and how this theorem can be used to obtain a kernel for vertex cover. And then, if time allows, I will speak about a little bit about lower bounds for kernelization. Okay, and this is a reminder from Tuesday, right? So on Tuesday, I end up my lectures with two theorems, classical theorems. One was the Koenig theorem, saying that in bipartite graph, matching, maximum matching is equal to minimum vertex cover, right? And you know definitely this type of theorems, max law, min cut, right? Linear program, so the minimization, maximization. So there are a lot of duality, but that's probably one of the first duality theorems in combinatorics. Okay, and again, so that was the algorithmic result. And also the other property of bipartite graphs and matchings and bipartite graphs, which I will be using, this is another famous theorem, Hall's marriage theorem, and I already explained why it's marriage theorem, right? Yes, and once again, so basically the thing which I will be using in the algorithm is the following property, that if I have a bipartite graph with bipartition A and B, then there is a matching from A to B, and I mean matching from A, which means that all vertices in A are matched in this matching, right? If and only if, so for every subset in A, if I take this subset and I look how many guys are adjacent in B to this set, this number should always be at least the size of, right? This is also kind of beautiful characterization of what is when I have a matching. And again, this is an algorithmic result, Hopcroft doing this in of m squared of n time. Okay, crown decomposition. So crown decomposition is the following object. Okay, so this is a graph, and in the graph I have a partition of the vertex set into three sets, C, H, and B. So Y C, Y H, and Y B. Okay, so C is the crown, if you see it right, H is a head, and B is the body of the king, right? So this is what mathematically speaking, what is that? C is an independent set. Then H separates C from the remaining guys. So there is no H between C and B. This is the second property. And the third property, there is a matching between C and H, which covers H. So there's a matching of H into C. Look, so C can be much larger than H. That's perfectly fine, right? And also H should separate C from B. So this is called crown decomposition of a graph. And this thing is very useful for constructing a kernel. Why? Okay, so let's take vertex cover. So, and for vertex cover, I can make the following crown reduction rule for vertex cover. What's happening here? So if I have a crown decomposition, then I have a matching from H into C. So this matching, if I'm looking for vertex cover, it has to be covered, so every H of the matching should be covered by vertex from the vertex cover. Right? Then what's happening? Because it's matching of H into C, I know that there is a, so my reduction rule is the following. I always can assume that all vertices of H go into vertex cover. Right? I remove the vertices of H from the graph, I remove the vertices of C of the graph, and I decrease my parameter K by the size of H. Again, why this rule is sound, right? I have edges here, and all these edges I need to cover by vertex cover. Right? And if and I know that all these edges, because of the matching, I cannot cover by less than H vertices. Right? So in any vertex cover, to cover these edges, I have to pay H. So why just I don't pay H by taking these guys, and because this is independent set, that will work fine. Right? So this is the reduction rule. Right? Everyone follows? Right? Good. Okay. So then the key lemma which I want to prove is the following. So if I have a graph G without isolated vertices and integer k, then in polynomial time I can do one of the following three things. First of all, I either can find a matching of size k plus 1, right? Or I can find a crown decomposition, or I conclude that the graph has at most 3k vertices. Right? This is combinatorial lemma. Well, algorithmic combinatorial lemma. Okay, so what's happening? So if suppose I have this lemma, right? And suppose I want to apply this lemma to design a kernel for vertex cover. Okay, so if I found a matching of size k plus 1, I can immediately say no, right? I cannot cover k plus 1 edges of matching by k vertices. This is a no instance. Okay, if I found a crown decomposition, I can reduce my graph, right? We had on the previous slide, we had a reduction rule, so I can apply reduction. Good. And if I conclude that the graph, or if my graph has at most 3k vertices, I'm also happy, right? Because this is a kernel with 3k vertices. Right? So if I'm able to prove this lemma, I will have a kernelization algorithm actually. Okay, so this is again condition of the lemma. Let's try to prove the lemma. So I construct greedily a maximal matching. Right? What means maximal? Maximal means inclusion maximal. So it's not maximal, it's maximal, right? So, and this is easy to construct. I just pick up an H, add it to the maximal matching, remove the endpoint, and then again try to find if there is an H, I add it. So this is a simple procedure, right? So if the size of this maximal matching is at least k plus 1, we are done here, right? Then I found a matching of size k plus 1. Done. Okay. If this is if this matching is of size smaller than k plus 1, then the remaining. So what's happening here? So I take the endpoints of the matching. The remaining vertices in the graph, they should form independent set, right? Because this is a maximal matching. So if there is a H living in the remaining vertices, I just can take this H and add it to the matching, right? So this is an independent set. Now, what I'm doing, I find I have a bipartite graph. So I form a bipartite graph. So one bipartition are the endpoints of the matching. And the second bipartition is an independent set remaining, right? And in this independent, I can find the maximum matching here. And I know by Koenig theorem that this is also the minimum vertex cover, right? Okay. And now what I argue. So if this minimum vertex cover, it contains at least one vertex in X, then I can find a crown decomposition. How come? Okay, so what's happening here? So I have this bipartite graph, and I have a vertex cover in part of the vertex cover living in X. Right? So this is vertex cover, and this is vertex cover. Then, if I take these guys as the head, and the neighbors of these guys in C as so the other endpoints of this matching is C, in C as the crown, then there cannot be an H going from here outside of H. Do you see why? Because if there is a H like that, this H is not covered, right, by vertex cover. So then I can construct, if there is at least one vertex in X, then I can use vertices in X to construct a crown decomposition. So I take these guys as a head, this guy as a crown, and the remaining part as the body. Okay, so I'm done here, right? Then I found crown decomposition. Or in the last case, what's happening? So I have this bipartite graph. This is the vertices of matching. This is an independent set. And then all vertices from vertex cover are here. in independent set. What does it mean, right? Well, let's try to see. Yes, so if there's no vertices in X and vertex cover, then all guys should be in the vertex cover here, right? But then, exactly. So we don't have matching of. Okay. So what's happening here, right? So this. So I cannot have more than k plus 1 vertices here, right? Because otherwise I have a matching of size k plus 1 or vertex cover of size k plus 1. So the size of this guy is at most k plus 1, and the size of this guy, right? This were the endpoints of at most k matchings. So the number of guys living here is at most 2k. So the total size of this graph is at most 3 times k. Right? So this means that the vertex cover admits a kernel with 3k vertices, right? Because what we are doing in the algorithm. So the kernelization algorithm is the following. I just take the proof of the lemma. And I run it, and at every step, in one situation, I find a matching of size k plus 1. I say, forget, this is a no instance. Or I found crown decomposition, I do reduction. Or if I cannot do reduction, this means that I have a graph with at most 3k vertices. Right? So this is a... And again, I will show that this is not the best you can get, but you will need a bit more machinery and different techniques probably to show it. Okay, let's just take another example. So every time when we have a... Yes?
You asked for having non-isolated vertices.
You asked what?
As a condition, you put non-isolated vertices.
Where? Yes, Martin, it's very good, very good. Yes. Yes, you're right, yes. It doesn't change the results, but I didn't pronounce important thing, right? Okay, so why I say that there's no isolated vertices here. So if I have isolated vertices, I can have them really a lot. And then, so if I didn't find the matching of size k plus 1, it's still fine. If I didn't find crown decomposition, it's still fine. Or then if I have a lot of isolated vertices, this is the last thing is not true. But if I don't have isolated vertices, then this is.
And you can create isolated vertices with the crown decomposition.
So yeah, I can, yes. So that's and this is then so then I have to come back to the proof of the theorem, and I should say the following thing. First of all, I always apply reduction rule. I delete vertices of degree 0, right? And this is important because otherwise what I was saying is not entirely true. And then after that I am applying the lemma. Yeah, thanks a lot. That's yeah. Okay, so as far as we have a hammer, right, crown decomposition, let's try to see what else we can do. And for example, take a look at max SAT problem. So max SAT problem, I have a CNF formula, phi, and integer k, and I ask whether phi has an assignment satisfying at least k clauses. Right? So this is again an incomplete problem. It's even max 2 SAT, where every clause is of size at most 2 is already NP complete. Okay, so the claim is that max SAT admits a kernel with k variables and 2k clauses. Okay, let's see. Well, first of all, why I always can assume that the formula has at most 2k clauses. Well, so the usual argument is that if my formula has more than 2k clauses, then it's always satisfiable, right? So there are several ways of proving this. It's probably the simplest one is I just take a random assignment of every variable, right? Then the probability that every clause is satisfied is at least 1/2. Right? So the expectation is that if I have more than 2k clauses, then the expectation is k, right? Which means that there always exists an assignment which satisfies at least k clauses, right? You can make this constructive also, right? This is there. It says okay. So I will. Okay. Now, if the formula has less than k variables, there is nothing to prove, right? So we have that it has at most 2 clauses, k clauses. So we are done here. Okay. Suppose that it has at least k variables. I construct a bipartite graph. So the bipartite graph, here are the variables, here are the clauses. And of course, if a variable is contained in the clause, I put an h. This is a, yes. Now, first observation. So if, so the number of variables here is at least k, right? This is what I'm assuming. And now, yeah? There's some, so it's not a question, okay. So if there is a matching from here to here, then we are done, right? Why? Because if there is a matching so which covers all variables here, so basically I can, so it means that this matching assigned to every clause is the unique variable. So this I can use this unique variable to satisfy this clause, this clause, this clause, and because I have k variables, it satisfies k clauses.
So but if the variable is negated in the clause, you could also...
But it doesn't matter. So if you have, look, so your variable can be negative in one clause and can be positive in the other clause, right? But what I say, I tell that this variable satisfies this clause. I mean that, well, if it's common in negation, then I put it false. If it's not negated, I put it true. Right? But because I say, okay, so this variable it can contain in many other clauses. But I don't care. So the only thing I want to care that this variable satisfies this particular clause. Right? So it's
you are trying to satisfy each clause with one variable somehow.
Yes. Because again, so if this variable satisfies this clause and it doesn't satisfy some other clause, I don't care, right? Because this is the clause I need to satisfy. The other clause can be satisfied by other variable. Yep. Okay. So what does it mean? So if there's a matching of x to y, we are done. So what does it mean that there's no matching of x into y? Okay, now we use whole theorem. By whole theorem, it means that there is a set of vertices C here, such that the number of neighbors of C here is less than the cardinality of C. Now, what I'm doing, I know that this set should exist, so I take inclusion minimal. Right? So no proper subset of this set C has this property. Okay. Because I'm using the minimality property of C and the whole theorem, right? Then I can claim that if I take any vertex x from C, then the C minus x, it satisfies whole property, right? Because of the minimality. This means that there should be a matching from C minus x into here. Right? Minimality plus whole theorem. Okay, but because C, so let's this be H, right? So because C was larger than H, right? That's what we assume. So we know that if there is a matching from C minus x to here, then also it means that these sizes of these guys are equal, and that there is also matching from here, from H into C. Right? There is a trick. So I was using this minimality trick here. Okay, but as far as there is a matching going from here to here, this already smells like a crown decomposition, right? I can take these guys as a head, these guys as a crown, and the remaining part as the body. Right? So I have a crown decomposition here. And let's see how I can use this crown decomposition for the reduction. So what will be the reduction rule? So if I have a bipartite graph, variables, clauses, this is the head, so this is the crown, and this is the remaining part of the body. So then what I'm saying, so I can remove, okay, and so there is a matching from here to here. And because of the property of the crown decomposition, no variable here is adjacent to any clause here. Right? So this part, it separates these guys from that guys. So this means that if I satisfy, so the only way I can satisfy these guys by using these variables, and I have matching from here to here, I'm doing this, and when I do an assignment of variables here, it doesn't interfere with the clauses here. So this is my reduction rule. I remove h from formula, I decrease k by the size of the h, and this is the new instance. So that's the proof of the theorem. Right? So this is what they proved.
So what again is the size of the kernel that you think?
No, but so what was my assumption, right? I was assuming that the number of guys here is more than k. And as far as I use this assumption, I come out to the Crown decomposition and to reduction rule. So this means that if I have a number of variables more than k, I can always use reduction, right? So when I can do reduction, it means that the number of variables here is at most k. So this means I have a kernel.
So, how do you find the set C?
How I find the set C?
Yes.
Okay, so good question. Yes. So by Hopcroft-Karp, so the whole theorem is constructive. There is an algorithm to find some set x such that the number of neighbors outside of x is less than the size of x, right? So I found this set, and now I'm trying to make it inclusion minimal. So what I'm doing, I just pick up any element, I remove it. If for the remaining part I have whole condition, that was the minimal set. If not, I consider again. So that's Hopcroft-Karp plus the greedy argument. Yeah. Okay, let's try to do slightly better kernel for vertex cover again. And the technique is also very old, not that old as Koenig and Hall theorems, but still quite old. It's called Nimhauser-Trotter theorem. Okay, so I hope that all of you are familiar with what is an integer linear program, right? So I just want to write what is a vertex cover problem as an integer linear program, right? So I write it the following way. So I have a constraints. So the constraints I associate with every vertex of a graph a variable, right? So and then these conditions means that for every edge of the graph, at least one endpoint should belong to vertex cover, right? This is condition that variables are 0 and 1s, and then I want to minimize the total size of the vertex cover. Right, this is a classical. Okay, so the usual thing when I have an integer linear program, it always makes sense to look at the linear program relaxation of this problem. And why? Because this is an NP-complete problem, and this problem is solvable in polynomial time. Right? So the relaxation of the problem, I just remove the constraint that the variables should be integer. So the variables are from 0 to 1. Okay, so I have a problem which is solvable in polynomial time, but solution here maybe is not solution here, right? Because solution here maybe it could be fractional, for example, and then what does it mean here? Okay. But for vertex cover, this integer program for vertex cover, it has a very nice property. So if I write the linear program relaxation for vertex cover, I can do the following things. I just fix some solution for this problem, and then this solution, it's automatically separate all vertices of the graph into 3 groups. So the first group are the vertices of the graph who receive fractional values less than 1/2. Then the second group, the V1, are the value of the vertices which received value more than 1/2, and V1/2 are the vertices of the graph which variables received value 1/2. Right? So this is a clear partition. And then, so the theorem of Nimhauser-Trotter says there is a minimum vertex cover. The optimum minimum vertex cover. Okay, there's a minimum vertex cover which we will call opt, such that this optimum is always, it includes all vertices V1, this one, and it's always contained in V1 plus V1 half, or V half. Right? So there are several variants of, some people say Nemhauser-Trotter theorem. This is the theorem which gives you two approximation algorithm for vertex cover, right? So the other thing is that people often say that Nemhauser-Trotter theorem says that there is always optimum solution which is a half integer. So there's the only solutions are 1/2 and zeros and ones, right? But again, so this is the variant which I will need, and this is the variant which I will prove to you, right? So what is the proof? Okay, so I have so here are the variables of my integer linear program. So here is v0 variables, v1, v12, and then I have somewhere I have an optimal solution. Right? Suppose I have an optimal solution for vertex cover integer for vertex cover linear program. So the solution say takes some guys from here, some guys from here, some guys from here, right? Well, let's take. Okay, so it makes sense to look at this set. So the set of the V0 vertices intersected with opt, and the guys V1 without opt. So what I want to do somehow, I want to swap them and to see what's happening. Okay, so let me define just the set opt prime, which is the set of opt when I remove all vertices from V0, and then I add all vertices of V1. So on this diagram, so what happened? I just take all guys from here, remove them, and I add all guys here. Okay, first of all, why it's still the solution to linear program? That's the first question, right? So why it's solution to linear program vertex cover? Okay, so the argument is the following. Look, what's happening here? So the vertices in V0, or the vertices which variables were V0, they should be independent set, right? Because if there is a H between them, so one endpoint is of value less than 1/2, the second endpoint is of value less than half. So the sum cannot be at least 1. Right? So there is no edges here, and well, I add vertices here. It makes only life better. Values here, and this part didn't change. Right? So this is also opt prime is also solution to the fraction to the linear program. Okay, but because optimum was the optimum, the opt was the optimum solution. For sure, opt prime should be at least opt. Right? What? Well, if this is like that, so if opt prime is equal to opt, we are done, right? Because we already constructed a solution to linear program such that all values are here and here, right? So this is a nice thing. Okay. And then I claim that if the opt prime is strictly larger than opt, then the fractional solution is not optimal. Right? So how come? Okay, so if opt prime is more than opt, then why, right? So the only difference is here and here, right? This means that the number of guys here, V0 cross opt, is smaller than the number of vertices or the number of variables here, right? So the only reason why this is not optimal. Okay, but then I just pick up a small epsilon, right? And small ones I just increase these guys by this epsilon here and decrease these guys here. And small means look. So here are all guys which values is strictly less than 1/2, and here all guys which value is strictly larger than 1/2. So I pick up epsilon, small such a small epsilon, such that all guys minus epsilon here are still larger than 1/2, and all guys here are still smaller than 1/2, right? This I can do. Okay.
So why this assumption? Can you go back?
Here?
The next one. That one.
That one.
That you say that the set of B0 and set of B-dot is less than, is the only possibility?
Yes, because...
that it's smaller, but it sounds more, no?
No, but look what's happening. So here,
So we can have that B1 less than of, okay, you replace B0 and set of B-dot with B1.
yeah, but I take one set, I replace it, and I have a better set, yeah?
But if you have that of prime rises because this set, okay, sounds more at the end because it's more than 1/2. No?
Sorry, so I think we're speaking about, so here I speak only about the cardinality, nothing else, right?
Why if op prime is, if you assume that op prime is greater than op, why the set is smaller than, why the cardinality of the set is smaller?
Look.
One possibility is
what is opt? Opt is the set of vertices. Okay, so what's happening here? So I increase these guys by epsilon. I decrease this guy by epsilon, and now just let's see that I still have a. And let's see that I still have a vertex cover here, right? And again, so I have to check that. Okay, so what's happening here? So this is an independent set, right? So there's no edges going here. So from A to B. There's no edges going from A to B. Why? Because this part was vertex cover. So this means that this A plus B was also independent set, right? So there's no edges coming here. And now if I look at the edges between B and C, and if I look between edges B and D, and B, so the edges between B and C. So every guy here was decreased. So if there was an H, right, the sum of the endpoints was at least 1, and one endpoint I decreased by epsilon, the second endpoint I increased by epsilon. So the sum remains the same, right? And then from B and C, B and C here, B and D. So these guys, so I decreased both endpoints by. Here I increase the endpoint by epsilon, right? But because this is still larger than 1/2, so the totals, and here is also larger than 1/2, the sum is larger than 1. It's okay. And then, yes, and the same is for B and E.
Sorry? Can you repeat why there are no edges between A and B?
Between, okay, so opt was the solution, and opt was look like that. Vertex cover, right? Right? And the complement of vertex cover is independent set. So there's no edges. Okay. Okay, so this is what we prove at the end, right? So this is, we prove that there is always a minimum vertex cover of G, such that this vertex cover contains all vertices with value V1, right? And it's also contained in all vertices with value V1 and V half. Right? This is a. Yep. But back to where?
Back to the what you were proving, no? No, before. Okay, so it's previous slide there. No, the previous one, yeah? Okay, so
Maybe we'll take it offline, right? Because otherwise, look, yeah. So it's like otherwise we will end up going through like. Okay. Look, so opt is an optimal vertex cover, right? And it's not this. Yeah.
no, the thing is that in the claim, that one, when you said opt is the cardinality of op prime. less than opt.
No, opt is a set of vertices.
Yeah, so
Opt,
what do you mean that is less than?
opt is a set. Okay, opt is a set of vertices. You're right. I have to put here, here, and here, and here cardinality. Yes, 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 yeah.
It's
Sorry.
not the value of the function.
Yeah.
Okay.
Good.
Yeah.
Now I understand. Yeah. And you're right. Yes, I write opt here like that. Yeah. I should put cardinality here. Yeah. Yes.
Okay.
Yeah. Sorry. Yes. Okay. So this is the theorem, right? So how this theorem brings us to kernelization? Let's try to see. Oh yes, before I go to kernelization, actually, I take carefully your comment on Tuesday, right? So about the running time of the algorithm, right? So if I want to use the Simhauser-Trotter algorithm or theorem as for kernelization, I need to solve linear program, right? And solving linear program is quite unpleasant thing. So the only thing that in this situation, it's also known that basically in order to solve linear program for vertex cover, it's the same as finding a matching in bipartite graph. So it's you don't have to apply all fancy techniques to solve linear program for this one. Okay, and then the other thing is also, so this the theorem I didn't prove that, but also with the similar arguments, you can always show that the linear program for vertex cover is a half integer. So it's always there is always an optimal solution which only has values 0, 1/2, and 1. But we don't need that for the algorithm, and I will not prove, so I don't need that. But this is just a nice thing to know, and it's not that often that when I have a rounding of linear program, I have a quite interesting structural solution. Okay, so now I can use Nemhauser-Trotter theorem to show that vertex cover admit a kernel with at most 2k vertices. Okay, so this is again, so this is the I write linear program, and I have vertices v0, v1, v1/2. So these are the vertices, and then I construct the following reduction rule. So my reduction rule is the following. So I take vertices with value 1/2, and I remove v0 and I remove v1. And then I also decrease the parameter by the cardinality of v1. Right, so the algorithm is the following. Write the program as LP, solve LP, use Nemhauser-Trotter to find LP, which is a half integer, and then this gives me partition of the... No. Once again, write LP, run algorithm on that, obtain partition of the variables or the vertices of the graph into 3 sets, remove v1, v0, and then yes. So why this is a reduction rule, right? So first of all, why this reduction rule is sound? So okay, let's see. Okay, so so if I have a vertex cover S prime in graph G prime here, right, of size K prime. Then if I take S prime and I add all V1, then I will obtain a vertex cover of size K, right? K prime, K is equal to K prime plus the size of V1. Right? And that will be vertex cover. Why? Because the set V0 is independent set. So, and that means that its complement is vertex cover. Right? So in this direction it's easy. Now, if I have a vertex cover S here of size K, right? Then I take the vertex cover S, and also by Nemhauser-Trotter, I can assume that this vertex cover S is contain all vertices here, and it doesn't contain a vertex from V0. Then, if I take S prime as equal to S cross V1/2, then I have a vertex cover here, right? So why this is a vertex cover, right? Because only ages lives here in 1/2, and which remains, and this and they are covered, right? And the size of this vertex cover, because of this, is exactly K prime. So this is the reduction rule. So the only thing what remains is to show that the size, if my graph is not reducible, then the number of vertices of the graph is at most twice k. So any idea why?
Because we have only now b1 half, right?
Yes.
And then if this is not less than k, this is the fractional solution.
Yeah.
Then you already kind of have that in there.
Very good. Yeah, yeah. Because yes, this is exactly what's happening, right? So so if I look at LP, right, there the only the vertices 1/2 left, right? And this there cannot be more than twice k of these vertices, right? Because otherwise I run out of my budget. Very good. Yes. So then it means that if my graph is irreducible, I have at most 2k vertices. And also, I have at most 2k vertices, but if I look at the number of edges in the graph, I cannot say anything meaningful. It still could be of order k square. And there is also some argument why it's like that. Yeah.
This is also a crowd decomposition, right? It's like B0 is the crown, B1 is the head, and B1 half is the
True,
body.
true, true. Nemhausen-Trotter is also exactly, that's also very good, yes. So that's very good, yes. So Nemhausen-Trotter, so yes, what Fedor is saying, that Nemhausen-Trotter is also gives me a crown decomposition, right? So so this is a crown, this is the head, right? And because there's a matching from here to here, it should be, and these guys, they are separated from these guys because there cannot be H from here to here. No. There cannot be H from, from here to here. Yes, exactly. Yeah, because it's here. Yeah. Good. Yes, this is exactly. Okay.
So but then can you take the same result by using matchings and?
But to obtain how to, it's.
To take the same result because here somehow you use LP, but with your previous few remarks, it seems that you're not using LP.
Yes, but the sizes are different, right? So there I was able to show. Yes, there is some magic part of linear program. Somehow it's it do a lot of job for you, and actually both results went on for a long time. And some people were asking if I can use crown to have a combinatorial proof that crown decomposition also gives you 2k kernel. And it's not easy, just try to play with that. So at the end, anyhow, what you will do, you will try to simulate the proof of Nemhausen-Trotter. But if you still, anyhow, you simulate the proof of Nemhausen-Trotter, why not just take Nemhausen-Trotter and use it for that, right? So it's but again, of course, look, it's vertex cover, and as I was saying, even to solve the linear program, you just use matching and bipartite graphs. So vertex cover, LP, is very strongly related to bipartite graph matchings. So this is there are things, of course, are related. Of course, okay. Okay. Okay, and I also want to speak just a little bit to give a glimpse what's happening with the lower bounds for kernelization, right? So I show you quite a few kernels of polynomial size. There were also kernels of exponential size, and we also know that FPT is equal to kernelization, right? But is there any way how to distinguish problems which have polynomial kernels and which have exponential kernels? So there are tools for that, but again, so I will just mention them very briefly. But let's just take a look at the k-path problem. So once again, what is a k-path problem? I have a graph, I have an integer k, and I ask if there is a path of length k in this graph. Right, this is a generalization of a Hamiltonian path problem, and also with color coding, I was given on Tuesday the algorithm of running time to the O of k. Okay, so then the natural question is, does k-path admit a polynomial kernel? Let's see, right? So suppose that it admits a polynomial kernel, and so suppose that this kernel has some, say, k cube. So Q3 here is just some number, so some constant, right? Okay, so just easy. Okay, then what I will do, so if I take, say, k to the 7 instances of k path, right? With different graphs, but with the same k. And suppose that, and I construct a new graph, I just take this joint union of these graphs, right? So then this graph contains a k path if and only if at least one of these graphs contains a k path, right? Now, suppose that I have a polynomial kernel for k path. So then I apply kernelization algorithm to the pair, to the parameterized problem hk, and then, well, I have a cubic kernel, that was assuming. I obtain a kernel with k cube vertices, and this means that basically this kernel is a graph, right? So encode a graph on k cube vertices, I just need like at most k to the 6 bits. And this is a very thing which happened, right? So basically, each of this graph, it's encode an p-complete problem, right? I just take any graph, I take parameter k, and then if I apply kernelization, I obtain something which has a smaller number of bits than the number of problems here. Right? I have k to the 7 instances and I have k 6 bits, which means that some of these instances in my reduced instance have 1 or 0 bits, right?
Sorry, but the new instances are the same. No, it's different instances. No, how you form the.
No, what I'm saying so far. So far, I just take a case to the 7 instances. They can be different graphs. They should be different graphs. But
Different graphs.
yeah, they're different graphs. I built a new graph. It's a huge graph. But then I say, oh, if there's a kernelization algorithm, let me apply kernel to this graph. And then I obtain kernel with k to the 6 bits. So I have k to the 7 and p-complete problems, instances of a p-complete problem, and I encode this to the k to the 6, which somehow means, right, that at least one of these instances you have to solve completely. And this is the intuition why k path cannot have a kernel, right? So basically, and but again, this is only intuition. And in order to yes, so the intuition that the final number of bits is much less than the number of input instances, which means that most of the instances has to be discarded completely, and this means I have to solve them, right? So this is something wrong happening here. And this intuition can be formalized, actually, so it was done in several steps. So first of all, there was a Fortnow and Santanow in 2008. So they define what is the OR composition of the languages, and they show that if you're able to compose some language into another language, and something bad happening. And then Badlanda and all, also in 2008, they used this for obtaining lower bounds. And basically, so the usual conclusion here is, again, it's I do not prove it, right? It's not complicated. It's possible to read, but it requires several clever ideas. So it's not trivial. Okay, and then so unless NP is a subset of co-NP / poly, then K-path doesn't admit polynomial kernel. And for those of you who don't, well, not comfortable with complexity, this is something which is well, it's something probably which doesn't happen. What does it mean? It's saying basically that verifying proofs cannot be simulated by verifying counterexamples, so in co-NP, which allows a polynomial advice. So, okay, so from engineering perspective, okay, it's not as bad as P and P. So if this is collapsed, P and P and NP is still maybe not true, right? But it's still also pretty severe. And for example, this implies that polynomial hierarchy collapses to the 3rd level. So basically, these things still can happen, but very, very much unlikely, right? So most people don't believe in this. So this is a kind of tool. And then kind of it's possible to use this technique to show that some problem so doesn't admit polynomial kernel up to this assumption. So this is what this assumption, and again, so this assumption is assumption. So why we cannot use, for example, assumption P not equivalent P? Again, because when we speak about polynomial kernelization, we speak about polynomial time algorithms. So we really are speaking about some structure in P hierarchy. So this is why we cannot use P and NP. But this is
but the K-path problem is noted is no no FPT, no?
It's FPT. I give you 2 to the k, 2 to the big O of k algorithm using
Ah,
color
okay,
coding.
okay, but the kernel is not polynomial. No, okay.
Yeah. It's,
Okay.
okay, so there is actually, if you go through this reductions more carefully and again use more ideas, so that was Dell and Mackelbeck proof that how actually to obtain even quality bounds on the exponent in the polynomial. For example, so they show that vertex cover doesn't admit a kernel of size k square minus epsilon for every non-negative epsilon. And you saw, right? So we had a kernel with 2k vertices for vertex cover. So this kernel has at most k square edges. So the size of the kernel is at most k square. Right? So this result is really tight from this perspective. So this is there are quite funny and interesting things happening there. Okay, so summing up. So what I was speaking about kernels. So after that I will go to a new topic. So Hall and Koenig theorems are nice and useful and still useful. This is a nice thing. So I spoke a little bit about ground decomposition, then integer linear program, and also I mentioned very briefly that actually it is possible to construct or to prove conditional lower bounds on the size of the kernels. And this is also now if you're doing parameterized algorithms and that you prove that some problem is FPT, the next step is immediately, so it's a kind of must that has to be done. You have to explore if your problem admits polynomial kernel or it doesn't. This is how it becomes very common in the culture. And if you want to read again, so this is the blue book contains a lot of kernelization, and actually if you really want to dive into kernelization, so again I'm using a small commercial, so this book is just appeared and I will put it soon online. Again we have with Cambridge University Press we have a contract which allows us to put this online, so that will be online. Okay.
But I'm a bit confused. In the K path you find a kernel list of 2K. Yes, and then solving that problem is polynomial time? Or
no. In the K path, I didn't find any kernel. In the K path, I just showed that this is FPT.
Yeah.
Right?
But the function of the
it was
the parameter is 2 to the K, no?
No. It was almost. It was 2e to the K. I was using color coding, so there are random algorithms, and then there was a dynamic programming. So but it's almost 2 to the K. Yes. For fixed k, it's polynomial, so that's why I'm saying it's hard to distinguish.
Okay.
Okay, and also we have an agreement on the exercises. So let me just, so for exercises for kernelization, so I suggest to solve 2 problems. So the first problem is cluster editing, so polynomial kernel for that. So what is the cluster editing problem? Cluster editing. Okay, input graph G, integer K, question, can G be transformed into cluster graph? And cluster graph, you know from the previous exercise, right? It's a disjoint union of clicks by changing at most k adjacent CS. So basically, I give you a graph and I ask if I can add or remove, but in total the number of operations is at most k. If this operation is delete h, add h, if my graph, if I can obtain a cluster graph, right? And the word of warning, right? I give you the kernelization algorithm for 3 heating set. So this time, this algorithm will not be useful because I cannot encode this problem as a heating set, because what's happening here, I have some forbidden subgraph, but then if I add edges, I can create a new forbidden subgraph. So you have to be careful here. Right? This is the first problem. And the second problem is so feedback arc set, fast, input, tournament, and integer k. Once again, tournament, again, you know it from the previous exercises, but tournament, once again, is a complete graph where I assign direction to the edges, right? And now I want to question delete at most k arcs to turn it into a cyclic graph. Right? And again, so hint here is the following. So while feedback arc set is always delete edges, so the good perspective here is not to delete edges, but change direction of the edges. So you have to show that for tournament, actually, it doesn't matter either you delete edges or you change direction of the edges. But why changing direction of the edges is much more handy as a reduction rule, right? Because in your reduction rule, you probably will need to change directions of the edges. Because you still, when you delete an edge, you're not in a tournament anymore, right? But if you change the direction of an edge, you're still in the tournament. This is one thing. And the second thing you need to know about a cyclic tournament is, but again, it's called, it's always admits a topological sorting, right? So you can always order the vertices of the tournament in such way, if there's no cycles there, right? Such that all arcs go from left to right. These are the two things, two hints, and I hope you will succeed there. Yes, and we still have like 10 minutes. So let me just, or any questions about kernels?
Do we know if the running time of FPT and kernel and size of kernel related somehow?
Sorry, what?
If the running time of FPT and size of kernel?
No. So this theorem which I was speaking that FPT is equal to kernelization, it gives me only exponential thing. But no. It's, okay. So I will speak a little bit about lower bounds, but what I will do here, there will be no computational complexity here at all. So that's so that will be completely algorithmic point of view how to prove lower bounds, and so there will be no Turing machines, no Turing reductions, anything. Okay, so but what I want to speak, so the plan for the lower bounds, I will speak about W1 hardness as a clique hardness. I will explain what it means. I will explain what is the exponential time hypothesis, and I will briefly mention what kind of ideas I use beyond exponential time hypothesis and how to prove these things. Okay, so the lower bound. So how we can prove that some problem, for example, clique is not fixed parameter tractable? That's one question. And the second question, if we have a FPT problem on hand, can we say something more reasonable? For example, can we prove that there's no algorithm of running time, for example, 2 to the small of k for this problem, right? And this is exactly what I want to discuss, so how to prove such things. Okay, so this is, yes, this is the only technical definition for the lower bounds, and beside that, that will be just nice reductions and things. But let's just, so the basic notion. So how many of you had a class on NP-complete problems? Just, okay, that's, yeah. So then you know that one problem is reduced to another problem, right? And basically, this is, you need to reduce one problem to another in polynomial time. But now I speak about FPT problems. So I want to have a parameterized reduction. So if I want to prove that I cannot solve this problem because I cannot solve that problem because there's a reduction, right? But that should be parameterized reduction. So what is a parameterized reduction? So parameterized reduction from problem P to problem Q is a function which maps problems from P to problems from Q. with the following property. So the reduction itself should be FPT, right? So to be meaningful. So the reduction is FPT, right? It means that it can be computed in time f of k times some polynomial of the input length, and where k is the parameter of this problem. And then also it should be so the mapping, right? So if I have a yes instance phi of x in Q, this is if and only if the x was a yes instance in P, right? So, and then the condition here that if I have a parameter here of x and k prime is the parameter of the image of the problem of x, then the size of the new parameter should be bounded by some function of k. Right? So why I need all these three conditions? Because look, if I have a parameterized reduction from problem P to problem Q, then if from an engineering perspective, what I can say, if there is a parameterized reduction from problem P to problem Q, and if Q is fixed parameter tractable, then also P is fixed parameter tractable. And again, so this is very similar to polynomial reductions. So the only thing that instead of polynomial time, I have to speak about parameterized reduction. And again, so this is, if you are optimist, you're viewing it this way, or you can view it that way. If there is a FPT reduction from P to Q, and if Q is, and if P is W1 hard, then so is Q. Right?
What if the third condition, somehow G can be a Riemannian function, whatever, no?
No, but look, so in order to say in this, so if Q is FPT, okay, let's see, right? So if Q is fixed parameter tractable, then I need to construct, so there's a FPT algorithm for Q, and I want to transform this algorithm into a FPT algorithm for P. So what I do, I take instance of P, I transform this reduction, and then I run the algorithm for this parameter. But if, because I evaluate the running time only as a function of the parameter, if I don't have a bound on k prime, the running time of the algorithm for Q cannot say anything about the running time for the algorithm for P. But if I have a bound here, I know that the running time of the algorithm for Q depends on some function of k prime, which also some function of k, right? And then I have FPT.
You compose the functions.
Yes, it is composition of function. Yes, exactly. Yes. So that's why I need this one. Yep. Okay. So now, if I want to prove lower bounds, right? So first of all, if I want, let's just try to relaxate a little bit on this. So if I have some problem, and I want to have an unconditional lower bound that the problem is not fixed parameter tractable. Would it imply that P is equivalent P or not? So suppose I'm able to prove those things without any condition. I give you a click, and the click is not fixed parameter tractable. Would it imply that P is not equivalent P or not? Look, so what will happen? So I have a P, I have NP, right? So the life is like that, and we don't know if this is separation, right? And now, so I have some like FPT, and I have a W1 hardness, for example, right? So if I show that problems here, they do not live here, I also show that problem which lives here, right? They do not live here. Right, so this will be, so definitely I shouldn't target for unconditional lower bounds, right? Just, I should lower my ambitions. Okay, good. Okay, so what will be then some evidences of negative results? And then it's actually, this is the philosophical perspective. And actually, this is the funny thing. So when I'm teaching a class on algorithms, or the basic class on algorithms, so there is always a chapter on NP completeness. And every time you teach the chapter on NP completeness, you have to define what is NP complete problem. And actually, when you check the exams, you see that that's almost every time this is a disaster, right? So it takes time. So for NP completeness, so but if you're doing algorithms, do you really care? So usually, of course, well, I'm doing algorithms, and I have to prove that some problem is NP complete, right? But do I need to know that what is NP complete? Do I need to know what is a Turing reduction? Do I need to know? Well, I need to know, right? But somehow I never use it in the proof. So the only thing what I'm using in the proof that I have some NP hat problem and I use in reduction. Nothing else, right? And basically, so if you even when you start teaching the course in algorithms, maybe the good idea is to say, okay, there are hard problems and there are just reductions between them. Right? So, and this is a kind of, yes, so there is a, let's just separate two different approaches. One, theoretical perspective, say like a NP-complete problem, non-deterministic Turing machine, Turing reductions, completeness, or there is just a pure engineering or algorithmic perspective. If I want to solve that, to show that the problem P is polynomial time is difficult, the only thing I need to show that there is a polynomial time reduction, which such that if I solve this algorithm in, okay, once again, what I need to show that if I can solve this problem in polynomial time, then SAT or any other favorite NP-complete problem will be also solvable in polynomial time. And this is actually, this is the only thing what usually people do in algorithmic papers, right? Just show reduction. So the same thing, yes. So what will be then this type of examples of parameterized reductions? So a bad example, right? So, or a non-example. So if I take instance of independent set, so the parameter graph G, and if I have an independent set of size at least k, then I know that I can always transform this into equivalent instance of vertex cover with parameter G n minus k. And if I'm looking for vertex cover as with parameter k, which is the number of vertices in the vertex cover, so then this reduction is not a parameterized reduction, right? Because n minus k doesn't depend on k. Okay, but if I say take an independent set and transform it into a clique by just taking complement of the graph with the same parameters, this is a parameterized reduction. And actually this shows that if clique is hard, then independent set is also should be hard. Okay, so what my plan will be for tomorrow, I will really start, I will give you several examples of parameterized reductions, and for that I will need a nice, yes, a problem which is plays the role of SAT in parameterized algorithms. And what I mean by the role of SAT in parameterized algorithms, when you speak about NP completeness, so the usual thing is you want to prove that your advisor tell you prove that this problem is NP complete, and you ask, but from which problem I have to reduce, and then the usual, if you don't know from which problem, do it for SAT, right? And in 50% it's true. So here it's actually even the situation is even more interesting. So for 90% of reductions, I know this is a problem which is called multicolored clique. So so if you want to prove the hardness of something, you don't need to know what is the hardness. You just prove the reductions for multicolor clique. Okay, and okay. So to be consistent, just we will start tomorrow from definition of multicolor clique, and then we will go for that. So do I should clap now?
Oh, yeah.
Okay. Now. No. Oh, please, this is embarrassing because I'm clapping not for myself, right? I'm clapping to synchronize with the audio. With the video. Okay, any questions about lower bounds you want to ask? Okay, then enjoy lunch.